So welcome everybody to this really very special occasion for our college. We have a huge number of people who have signed on for this event, which is being run in partnership with the Oxford Mathematical Institute. We have people who matriculated from 1948 to 2020 joining us. So that's about as broad a spread as is physically possible. And we're here to celebrate Sir Roger Penrose. It's quite difficult for me to describe the level of delight that passed through our college when we heard the news late last year that Roger had been awarded the Nobel Prize. It was an extraordinary moment for him, but it was an extraordinary moment for us. And we flew the flag, we were delighted, and we were proud of Roger and of our association with him. Roger, as you all know, is a mathematical physicist, a mathematician, a philosopher of science, and a Nobel laureate. He is Emeritus Rouse Ball Professor of Mathematics in the University of Oxford, an Honorary Fellow of St John's College, Cambridge, and of University College, London. Most importantly, he's an Emeritus Fellow of Wadham College, where he was a Rouse Ball Professorial Fellow for many years. And I'm delighted that we're joined by one of his successors tonight, Professor Fernando Alday, who joined us very recently and I hope is settling in. We're delighted to have him.
Thank you.
To be frank, Sir Roger has so many awards that if I mentioned them all, we'd never get to our conversation. So I'm just going to mention a few. His election to a Royal Society Fellowship in 1972, his receipt of the Royal Society Royal Medal in 1985, the Albert Einstein Medal in 1990, his knighthood in 1994, his appointment personally by the Queen to the Order of Merit in 2000, the Copley Medal in 2008, and his award, the Nobel Prize for Physics in 2020. This is our opportunity, Roger, to express our delight and our congratulations as a college community gathered from all over the world for your wonderful achievements and for the richness of your intellectual life over decades. So thank you very much for being with us this evening. It's a great honor for all of us.
Well, thank you for your introduction.
We're going to later play a recording of Roger's interview, the conversation with Wadham Honorary Fellow Melvyn Bragg. I've been asked to say that if you have any difficulties with the sound or the image, you can access a direct link to that conversation via our homepage. But first, I'd like to speak with Roger briefly, if you don't mind, Roger. Can I ask you this before we get to some of your work? Looking back into your early childhood, if you don't mind me asking you to do that, was there a time when you recall first becoming aware of the mathematical world? Is there a moment that you can point to that sparked your interest, or when you were first aware of your interest in that world?
I think it came pretty young. No, first, that's a difficult question. Oh gosh, I can remember certain specific things which picked up my interest. One in particular was, I remember there was a tiling on either on I can't remember whether it was on a floor, on a sink, which is regular hexagons, and they were just covering the plane there. And I looked at this and I asked my father, suppose you continued this pattern all the way around the Earth, could you make it the same pattern continue all the way around the Earth? And he said, no, you can't do that, but you can do it with pentagons. And what he meant, you could make a dodecahedron. So we then got together and constructed all the regular solids and things like this, and some truncated ones and various things like that. So I certainly picked up interest. I had an interest before that, I know, but try to point to anything particular a bit difficult.
Hmm.
I think I learned, yes. No, let's. Someone pointed out, is I had a little story, which I don't know whether you call this an interest in mathematics or geometry, but when I was young, I couldn't stand spinach. I changed completely because I love spinach now, but when I was very young, I was probably about 6 or 7. And we had a nurse or somebody who was looking after us, and she wanted me to eat my spinach, and no, I wouldn't. No. So then I said, well, how about if I just eat half of it? And she said, all right, that's good enough. Just eat half of it. So when she was out of the room, I took this patch of spinach and made it into an exact semicircle. And then I didn't eat any of it. And she came back and she said, that's fine. And she went away again. So I don't know whether you can consider this an interest in geometry.
You probably could. An interest in geometry and disinterest in spinach at that time. I think it's interesting. Everyone used to hate spinach. Now everyone loves it because it's so healthy and it's cooked in a different way. It's not soggy anymore.
I think that's it, yes. No, I love it now, yes.
But your early life, I mean, you have a brother who's a physicist, a sister who's a geneticist. Your father was a doctor. So was your childhood? I know there was art as well in your family, but was your childhood quite sciencey? Were you talking about science? Were your siblings interested in science from an early age?
Oliver certainly was, my older brother, and he was very precocious. He was about he was 4 years ahead of me. He was 2 years older and 4 years ahead of me in his schooling. And I learned a lot from him because he understood a lot about physics and mathematics. But I think more important, it was with my father, because although he did human genetics, he had a love of mathematics, particularly geometry, I think. But and we used to go for walks and things like that, and he would talk about maybe the plants and how the Fibonacci numbers arose in them and so on, things like that. So, and I certainly gained a lot from talking to him. Not just the polyhedra, which was one thing, but other things in mathematics. And also from my older brother, because I remember, yes, I remember noticing, I'll probably get this wrong when I say it, but I'm noticing that when 2 + 2 = 2 × 2, you see, I was a bit struck by that. And I wondered if there were any other numbers like this. And so I came across, what is it now? I'd have to think. Is it 1/3 and 1/2 and no, it's one. That's right, 1/3 and no, and 3 or something like that. I have to think what it is. Sorry, I'm off my head at the moment. Yeah, 1/3 and 2/3 make 1. So it's 3 and 1.5. Is that right? The sum of them is also equal to the product of them.
Mm.
So I noticed that, and I sort of played around with this and wrote down some complicated equation, which I'd sort of worked out geometrically. And I asked my brother about this, and he said, well, look, it's just equivalent to this. It's that you take, if A + B is equal to A times B, then 1/A + 1/B is equal to 1. So you just divide 1 into 2 bits like that and take their reciprocals. So I was very struck by that, and how you would get that from the complicated formula I had. And so I learned a lot of algebra from him in that respect too. I don't know how old I was then, but that was probably when I was in my early teens, I think, probably.
But there was a lot of art in your family as well, wasn't there?
Well, my father was very artistic. He was a very good artist. Sometimes he would like to go sketching, and sometimes I would accompany him sketching too. I think pen and ink was his real skill, but he did watercolors as well, or oils. But his father was a professional artist, James Doyle Penrose, who he tended to paint very religious pictures. He was a very religious Quaker. My father came from a Quaker family. My father was not religious, but he was certainly followed some of the Quaker practices. But one of his brothers, I think there were 4, he and 3 other brothers, all pretty artistic, but Roland in particular became a big figure in the art world. He was very important in the Surrealist movement in Britain, and the Institute of Contemporary Arts, I think, he was one of the founders of that.
Do you think art can have a role to play in conveying scientific ideas?
Oh yes, well I hope so, because I like to use it. Things
yeah.
like
I was going to ask you about that.
I tend to, in my semi-popular books, I tend to draw all the drawings, and unless it's something particular for computer drawing or something. But otherwise, I would draw all the pictures. Yes, and the idea is that this is conveying mathematical ideas or physical ideas in terms of pictures, which is part of, I think, the way to convey information to people.
I want to come, if we can, to Wadham and your arrival at Wadham. It might be thought that it's particularly apt that you came here because it's the home of the Oxford Philosophical Club and those wonderful mid-17th century polymaths, Wren and Hooke and Wilkins, who went on to found the Royal Society. Yes. But these men were polymaths, and Wren was a mathematician, an architect, an astronomer, and they had this strength across disciplines. And I wonder whether you see yourself in that sort of tradition, that cross-discipline tradition.
Well, I'm very flattered to be compared with Wren. And no, I certainly knew about him and that he was connected with the college too. Yes, and the Royal was one of the origins of the Royal Society. Yes, I appreciate that too.
And that idea of cross-disciplinarity and colleges in Oxford and Cambridge bringing disciplines together by enabling fellows to get to know the work of colleagues in different fields. Is that something you found at Wadham? Is that something that you found useful, energizing?
I'm trying to think. Yes, I'm sure. I mean, certainly the kind of thing, like this cross-discipline aspect of it. I mean, there are certain things I'm a bit, I mean, certainly science and visual arts was something I enjoyed. Writing as well too. I always thought I had a blind spot with poetry. I can appreciate it, but not to the degree which I feel. So there's, I don't know, it's not, but I certainly found Wadham was very much in that direction, yes. And I remember Stuart Hampshire, who was the warden at that time.
Possibly, yeah.
And he used to have meetings. I remember he used to go to dinners he would have, or lunches, I can't remember whether lunches or dinners, when he had lots of guests, and they were very stimulating occasions, I remember.
Well, in the same vein, I wanted to ask you about this. You obviously in your career, Roger, you've contributed to many different, sometimes unconnected areas of science, and this is probably a question that could be put to all polymaths, but do you feel your success has come from seeing how techniques from one area can be exploited in another, or is there more to it? Do you see the problems you've worked on as different aspects of some more fundamental question about the nature of reality?
It's a difficult question. I mean, a lot of things which I do, which seem rather disconnected, are actually connected, and the ideas do clearly relate one to the other. But one thing which hasn't quite so much done this is the non-periodic tilings. I mean, you have an example of this. I haven't been to the college for quite a while, but in front of the student.
In front of the student bar, we've got the Penrose tiling on the ground. Yeah.
So that's an example.
Yeah.
I think the college was one of the earliest to use one of these designs.
Yeah.
But the Mass Institute now has a very elaborate one.
Yeah.
Designed specifically for the pattern. The tiles are the same shapes, but the pattern on the tiles is very different.
Do you one of the things I wanted to ask you about was your work on, I suppose, what some people might think is the greatest mystery, which is consciousness, because I guess it's in that area that you have dipped into various different disciplines to come to conclusions, and it's very polymathic work, if I can put it that way. And it's something that everyone asks themselves about. What is it? What is consciousness? How does it arise?
Well,
what is it?
Big question, yes.
That is a big question, but I wanted to ask you, what is it? What is consciousness?
It was almost a forbidden question, I seem to remember, by scientists. It was thought, shouldn't dabble in that. I think it's changed. You see, it really arose from my, when I was at Cambridge as a graduate student, and I thought, 3 years, that's a lot of time. I don't have to spend all my time working on my particular thing. And so I decided to go to various lectures, which were not specifically to do with my topic. One was a course of lectures by Herman Bondi on general relativity, wonderful course. And he was very demonstrative and active and very entertaining. And there was a course by Paul Dirac, very difficult and very different in style, but also wonderful lectures, I thought. And then another course I went to is by a man called Steen, and this is a course on mathematical logic, because I'd learned a bit about mathematical logic, and one of my colleagues when I was at University College as my undergraduate work, I had long conversations with Ian Percival, who we talked about all sorts of aspects of science, but one of them was to do with mathematical logic. And I remember hearing about Gödel's theorem, and it seemed to tell you that there were things that you couldn't prove in mathematics, and I didn't like that idea. So I went to this lecture by Steen, and he talked about Turing machines and computability and things like that. And then he talked about the Gödel theorem. And I was absolutely stunned because, well, you see, it's something, if you've got a specific set of rules, you've got some axioms and rules of procedure, how do you know whether something is true in mathematics? So you might say, well, the proof will be following these specific rules. And what Gödel shows is as long as you trust these rules to give you truths, and the whole point of a proof is that it gives you some, if it says, yes, it's true, then it is true. Then you looked at the rules and you've looked at the axioms and all this and say, yeah, yes, I accept all that. And anything you derive using those procedures has to be true. And it's your trust in the system that it gives you only truths that allows you to extend beyond the system. So that's what Gödel does. He shows you a statement and you can see it's true. You can see it's true by virtue of the way it's constructed. But you can also see it's not provable by the rules that you've been given. So it's not provable. If you thought that mathematical proof was only following these rules, then you miss things. And how do you know this thing is true? Well, it's by the same reasoning or understanding or whatever it is that leads you to believe that following the rules gives you truths. And I found this absolutely stunning because it showed to me that understanding, whatever it is, the quality of understanding, which is one of the features of consciousness, is not a computational thing. Because these rules of procedure and all that, that's basically a Turing machine. You see, anything which has this kind of logical form, you could put on a Turing machine, and this means you could make a computer do it. So you could put these rules on the computer. But since it doesn't have any understanding, it doesn't know what it's doing, it's just following the rules, it falls short of the things that with understanding, you can see are true. And I thought this absolutely amazing. So I formed the view that whatever is going on in our heads when we consciously understand things, look, we do lots of other things with consciousness, not just understanding, but I'm only concentrating on that one quality. This quality of understanding seems not to be something that is a computational thing. I wrote my book, The Emperor's New Mind, making this point. And I got in a lot of trouble with people who, and it's endless and it's still true, mainly because I think they didn't understand the arguments. And I wrote a second book, which was The Shadows of the Mind, which was meant to address all the complaints that people had made. But then still people weren't happy. But then I think, see, the arguments get terribly contorted. And there's a much simpler argument. And this is more an argument from natural selection, because you see, okay, you can see these things are true by this complicated way of playing with logic. But if that was a result of some algorithm that we didn't know, you see, the thing is that maybe it's an algorithm or a computer that we don't know. It's just evolved in our heads, you see. Now, how could it evolve in our heads unless it was of value to us in natural selection? But these things that you can go beyond our the most primitive understanding of mathematics are not anything you possibly have got through natural selection. It's just not anything like it at all. So it seems to me that the argument is a pretty strong one, even though very few people follow me in this argument. So I've always found this a bit irritating that people don't follow me in this argument, but they think, you know, okay, I don't understand how powerful computers get. Well, I do understand how powerful they get, but I still think they don't understand anything they're doing. And the understanding has to come from the human being. but then what's going on in our heads? And I never thought it was some, mysterious magic that comes in from, or something more akin to religion or something like that. I thought it's science. So then I thought, what kind of science can it be? Well, not Newtonian mechanics, you could put that on a computer. Not general relativity, you could put that on a computer, where you get these, as we now see, these LIGO picks up these very signals and can analyze the data of those. And these are things that you get from computations of what black holes spiraling into each other give you and all that sort of thing. So, okay, general relativity, it may be hard to do, but you could put that on a computer. What about quantum mechanics? Then I remember this lecture that Dirac gave. And at the beginning, he had a piece of chalk. No, I think he was talking about the superposition principle. He said, an atom can be here, or it can be here, and in quantum mechanics, it can be here and here at the same time, in all sorts of different ways, here and here at the same time. And then he took out a piece of chalk, and I think he broke it in two to try and illustrate it being in two places at once. And then he gave some argument about why this wasn't a problem. But I was sort of daydreaming at that point, looking out of the window and thinking of something else. So I missed the argument completely. And then I remember him just talking about something about energy afterwards. And I have no idea what his explanation was, which is probably just as well, because I have a feeling that his explanation would have been something to calm you down and not worry about the problem. And but that I worried ever since. And I thought, well, it must be this thing, which is called the collapse of a wave function. And that's what's going on. So when I think about what's going on in conscious thinking, it's not just the ordinary picture of nerve propagation, which doesn't give it. There's got to be something else. And so then I wrote this book, The Emperor's New Mind, hoping that I could learn something about neurophysiology to make the case for what that was and try to see what it is that could be going beyond standard computational procedures. And I didn't. I learned about the standard procedures for how nerve transmission was supposed to go, and it seemed to me that it's completely hopeless from this point of view. So I rather ended the book on a weak note and hoped that I'd get away with it. But Stuart Hameroff, who was what they call an American anesthesiologist, anesthetist, so his job was to put people under general anesthetics. But unlike most of his colleagues who just wanted to make sure that people woke up afterwards and weren't damaged or whatever it was and didn't experience the pains, he was really wondering what on earth he's doing when he's making people go unconscious. And so he was really scientifically interested in what's going on. And he formulated some ideas. But when he read The Emperor's New Mind, he thought, first of all, there's something evidently I didn't know, which was true. And that here was something he'd never heard of, this idea that you could have non-computational procedures. And so he told me about microtubules, which I hadn't heard of before. And this is something that goes beyond the standard Huxley, the standard theory about how nerve propagation works. And only very recently, we'd had some communication about this. And there are certain particular cells. See, one of the things that always puzzled me, that the cerebellum, this part of the brain which goes under, and there are more neurons in the cerebellum than there are in the cerebrum. Yet it's completely unconscious. And what is it that makes the cerebrum conscious where the cerebellum is unconscious? And Stuart says, well, there are these pyramidal cells, there are particular types of cells which are in the cerebrum and not in the cerebellum. And he thinks that that's the main place where the conscious action takes place, and that you can work out how the nerve propagation and then the standard procedures for nerve propagation are violated. It doesn't behave according to those rules. So I think one can make some progress on all this. It's probably a long way off, but still. Excuse me.
But your conclusion, one of your conclusions, is that however powerful computers become, they're never going to be as powerful as a human brain in the sense of lacking that fundamental quality of understanding.
That's right. It just doesn't have it. Well, you saw I constructed a chess position, you see, which was a completely stupid position. I never liked to play chess because I had a younger brother who was much too good for me. And he then became British chess champion a record 10 times eventually. But anyway, so he used to beat me at most games. But so that sort of, I was glad about that because it immunized me against playing chess, which was
Can I ask you about the usual interactions back and forth
yes.
that take place in science between theory and experimental observations? Famously, you can't win the Nobel Prize for Physics for pure theory. Your theory has to be proved, which is why you waited from 1986 from the publication of your groundbreaking paper to win your prize, because it
was 65.
65, sorry, 65.
Yeah.
So can I ask you this? And this may be binary in a way that's not accurate, but was your work there driven by the desire to explain astronomical observations at the time that suggested black holes really existed, or conversely, were astronomers emboldened to go and look for black holes or reinterpret them because of your seminal paper?
I think it's both ways, but it was
Yeah.
more particularly the first. That is to say, I mean, I was interested in the ideas of black holes before that. I remember going to a lecture by David Finkelstein when I was in my second year, I think it was, as a research fellow at Cambridge, at St. John's. And there I sort of learned the picture of, well, collapse to a black hole, which was known already. There was a paper by Oppenheimer and Snyder in 1939, where they described the collapse of a dust cloud, and it would get to this form, what we now call a black hole. But very few people believed it because it was, well, the main thing was exactly spherically symmetrical. And the dust cloud was called dust because it means it doesn't have any pressure. So everything just falls towards the middle. And so there is nothing to stop it. And so, okay, if it builds up in the middle to form infinite density, so what? Because a realistic body wouldn't be like that. It would swirl around and maybe come swishing out. That was the sort of thing people thought. So that was a sort of round, but it was really the quasars. They were called quasi-stellar objects originally. And these were radio sources initially, which were extremely bright. They were about maybe 100 or 1,000 times as bright as an entire galaxy, but yet they had variations to tell you that they couldn't be much bigger. Well, they couldn't be as big as the solar system. And this meant that the amount of energy coming out would require a lot of mass there. And so you imagine that mass concentrated in that region. And people started to think what happened when you got this gravitational collapse of bodies, maybe collections of stars, maybe single stars, but I think more the collections of stars was what was the thing that interested me. But this was an observation. There was something going on. And so I began to think about this problem, begin to think about it. But John Wheeler, who I'd worked with, he was in Princeton, in New Jersey, and he was very puzzled by this question. Well, I think he thought you wouldn't get these singular states in the middle. They come swirling around and come out again. And so he asked me what I thought about it, and I then got together and started thinking about ways I'd been thinking about other problems. You see, I think the thing was, I like to think these things through myself. There was a paper at the time by two Russians, Lifshitz and Kalatnikov, and they appeared to have proved that generally you would not get this singular point in the middle. They just swish around and come out again. There was actually a mistake in the paper, which I didn't know and I didn't see. I did look at the paper, rather. I didn't look at it in full detail, but I just got the gist of the kind of thing we were doing. And I wasn't convinced that you could find a fully rigorous argument that this was what was going on. So I thought I'd try to think about it myself. And you see, what people were doing at the time were either finding exact solutions of the Einstein equations, and mainly this was done in mathematics departments, certainly in Britain. I did a bit of that, but not very much of that. But the other way people would look at problems was put them on computers. And at that time, certainly they couldn't have got very far. Even now, you can't really tell where you've got a singularity. It may be just the computer has got stretched beyond its capabilities. So it's a bit hard to get information like this out of a computer simulation, which certainly wouldn't have been possible at that time. But I was thinking about these things in a much different way, very geometrically, and thinking about how light rays focused. I think one of the things was my experiences at school when we used to play with these what do they call these? You put lenses on a track and you move them around and see how the focusing is affected by the lenses. Optical bench, is that what it's called? I forget the term now. But anyway, so I got some experience from what lenses did. But then I realized that to see how light rays behave in general relativity, it's important to see how they get focused by lenses, and also how boundaries of futures sets behaved. I mean, I was just playing around. Yes, the first thing, not the first thing, but I think the thing where I developed certain techniques from a completely different problem. I was looking at a problem which eventually became a paper I sent to the Proceedings of the Royal Society. It was published at about the same time as the Nobel Prize paper. But this was about something else. It was about radiation, how it behaves in long ways off, and particularly not just electromagnetic radiation, but gravitational radiation. And I proved some theorems about how it behaved and how the curvature tensor looked, and some interesting properties that were known at the time, but this was a much better way of doing it. And to prove something, I had to realize that the structure of infinity looked like a sphere. That's a bit hard to say what I mean, but you see, if you look out the sky looks like a sphere. And I was thinking in the future, you say you have a cone of light going out to the future. Does the infinity which it reaches, does that look like a sphere? And I need to have that. When I say look like, I mean topologically. It can be a wobbly sphere with bumps on it, but it needn't be an exactly spherical one. That doesn't matter. But it mustn't be a torus or, you know, like a donut, something like that. And so I put in an appendix in this paper, which I thought was a complete waste of time. But I developed techniques for showing that it had to be a sphere. And this was using the techniques that I developed, putting in an appendix, which I thought was an utter waste of time, because nobody would bother that. We just say, well, assume it's a sphere. That's the obvious thing. But I was just fussy about it, and I thought I needed to make sure this was completely rigorous in that respect. And the techniques that I had used there and put in that appendix were crucial for this argument that I used for the paper that got the Nobel Prize, because it was looking at what futures of sets look like. You see, you've got a region in space-time, and the future of that is the things which it can influence. So the light rays from it are the limit of what can do. And this boundary can be very complicated because the light rays can cross over and form caustics and do complicated things like that. But using the types of arguments which I'd done for my appendix, I realized what boundaries of futures look like. And then I was having a discussion with later on, I was a lecturer at Birkbeck College in London. And I was, I think, talking to a colleague of mine who was an Englishman who worked in Dallas, Texas. He's Ivor Robinson, who was he was very skilled at producing exact solutions of Einstein's equations, things like that. But he was also somebody who did it all verbally. He never wrote, I think he wrote one paper or something himself. They were always jointly because he got other people to write the papers. So he did it all by talking. And he was chatting to me, you see. We were walking along the street, somewhere near one of the parks there. And we came to a cross street. And as we crossed the street, the conversation stopped. Then it started again on the other side. And he then started up a conversation again like this. Then when he left, I had this strange feeling of elation, which I couldn't pinpoint. I thought, why do I feel like this? And it was nothing to do with the conversation. So I went back to everything that happened in the day. Was it what I had for breakfast? Did I get up the right side of bed or the wrong side? Or how did I take, was it the tube or the bus? Or did I walk through the woods to come? Or all that sort of thing. And then I got back to work my way through to this crossing of the street. And I realized I had this idea, which is what I later called a trapped surface, which is a characterization of a collapse of the material, which is not dependent on it being regular at all. You take the regular case where it's actually spherically symmetrical, and then you can find this trapped surface just outside the matter. And then you wiggle it a lot and it's still a trapped surface. And then I was able to show that if you have a trapped surface, then you have these singular points where the curvature goes crazy or something like that happens. You can't tell what happens in detail, but it's what we call a singularity where the equations go wild. And
you had that idea crossing the road.
yes. Well, I didn't have the full argument. I then went back to the office and I saw that, yes, I could use it. I just thought it was a promising thing to use, the trapped surface.
Can I just, before we finish, because we can't take more of your time, I just wanted to ask you about reasoning and the importance of reasoning, and how things go wrong sometimes, not because people don't understand basic mathematical operations, but because they don't understand mathematical reasoning. There are plenty of examples, incidentally, in my own field of criminal justice, where statistics and probability are very widely abused and lead to very damaging consequences for some people. But it's also been true in finance, and we've seen that it can be catastrophic.
Yes,
there and in other walks of life. Do you think education should give people a stronger foundation in mathematical reasoning as opposed to simple numeracy? And how would we best introduce those concepts to young people?
Not a bad suggestion. I mean, thank you. I think that's a very good suggestion. I don't see why people shouldn't learn about certainly basic mathematical logic. I mean, to get as far as Gödel's theorem is a little tricky. Actually, you could do it, you see, with not the way Gödel did it, because it was very involved. But basically, once you have the idea of a Turing machine, which is not so difficult to understand. I mean, you can think of logic, which is ordinary logic, you know, with things like A and B, and A or B, and then you can have what people call Boolean algebra. And then you can do a sort of algebra which simplifies logical statements like this. And then you have the quantifiers and things which say something is true for all x.
Yeah.
There exists an x such as something is true, and that's really the basis of mathematical logic.
So you could start by teaching some form of logic in schools.
Yeah, I don't see why not.
I think they do in France, actually. I think in some continental countries they do it.
They probably do. I guess I don't know why they don't do it here. I think it's an excellent idea. Yeah, and it's a fascinating subject because you get into these things which look like paradoxes. They're not paradoxes, but they're really showing you sort of the power of reasoning, of understanding what you're doing.
Roger, it's been a fascinating discussion. In fact, we've overrun. It's been a real pleasure speaking to you, and an enormous privilege for all of us to
We got a bit too technical.
To listen to you. No, it didn't get too technical at all. Actually, I thought what you were saying about consciousness was fascinating. As you say, I think you've written 3 books on the subject and stirred up a bit of controversy. But it is a endlessly fascinating topic, and your contributions to it, as to other fields, have been enormous.
I think we're a long way from an answer to that question.